All right. So last time we met, we were using the molar mass, which is the grams of material you need to weigh out to get a mole of something. And we're using the molar mass and our new number, the magic number for what a mole is. Remember, it's kind of like the word dozen. We use the word mole to mean 6.02 times 10 to the 23rd, or whatever it is. So instead of 12 for a dozen, it's 6.02 times 10 to the 23rd. It's a big number because chicken farmers needed to work in dozens because, they couldn't afford boxes with 1 egg, 2 egg, 3 egg, 4 egg, so they needed to always sell in large numbers. Chemists need to work in dozens, or not in dozens, but in moles, because if you had to work in smaller amounts, the number of boxes would be infinite and you wouldn't be able to get anything done, right? So we work in moles. Percent composition is another way that we express information about the amount of different elements in a compound. So here's an example of a compound. Can you tell me the name of this compound here?
I don't see anything.
Oh, you don't see anything. Sorry about that. Hold on.
Okay, sodium carbonate.
Hey, really good. Way to go. That's great.
Well, let me ask, or would it be sodium tricarbonate? How do I tell the difference?
Okay, now there is no difference. There's no such thing as sodium tricarbonate or sodium dicarbonate or disodium carbonate. Okay. Remember.
And how? Okay.
How do we know? Well, because let me bring up my periodic table here. Where's my periodic table? I gotta get it. The sodium, look at our periodic table, and we'll see that sodium is a representative element on the periodic table. It's from the first two lines. And so we know what its charge is always going to be in an ionic compound. It's always going to be a +1. So we don't need any other naming mechanism to name it, right? Okay, so sodium carbonate. Now, when we say sodium carbonate, chemists will know that we're talking about this compound, Na2CO3, all right? And we also know that when somebody's talking about sodium carbonate, they're talking about 2 ions of sodium and 1 ion of carbonate. Whenever we're concerned about what this is, we can look it up on the back of our periodic table, our polyatomic ion chart, and refamiliarize ourselves with the charge on it, right? Sodium ions, like we just went through. We saw that the periodic table helps us remember what the charge on the sodium ion is, okay? So this is stuff we know. We also know, for example, that in 1 mole of sodium carbonate, we can say there's 2 moles of sodium. In 1 mole of sodium carbonate, I can say there's 3 moles of oxygen. In 1 mole of sodium carbonate, I can say there's 1 mole of carbon, right? In 1 mole of sodium carbonate, I can say there's 3 moles of ions. 3 moles of ions, right? So I have lots of different... Yeah.
Can we...
Yeah, so the 3 moles of ions for every mole of sodium carbonate. And all of these statements about the number of atoms of sodium per mole of sodium carbonate, the number of atoms of oxygen per mole of sodium carbonate, the number of sodium ions, the number of carbonate ions per mole of sodium carbonate, right? These are all stoichiometric statements, right? Stoichiometric is the word that we use when we're talking about kind of the relationships. And we can make conversion factors, right? We can say 2 moles of sodium for every 1 mole of Na2CO3, right? And that sort of conversion factor can be helpful in answering questions, solving problems. Okay, another way that we can think of the amount of sodium in sodium carbonate, for example, is what we call the percent composition. Percent. And sodium carbonate is 43.38% sodium. 43.38% sodium. Now, where does this percentage come from? Well, it comes from mass, just the mass of the sodium in the sodium carbonate. Now, do you remember how we would identify what the mass of 1 mole of sodium carbonate is? Remember how we do that with the periodic table?
We look, yes, it shows the atomic mass.
And what if we're looking for sodium carbonate, what atoms do we have to look for then?
So we're looking for the, I can't quite read the mass here. It's kind of,
on the sodium?
where is it? Yeah.
Okay, it's like 22.9, right? So the little one down there, 30 or 23
Right.
grams per mole, right?
Right.
Okay. So two sodiums.
Yeah. Okay.
So we got 2 sodiums. That's 23 twice, 23 times 2, right? And then we have 1 carbon. Do you see the mass for carbon?
Uh, 12.
Yeah, 12. And then how many oxygens do we have?
We have 3, and they're each 15.
15.99, so
16.
pretty much 16, right?
Right.
Okay, so we put that in the calculator, and what do we got here? $106. 106. That's how many grams, 106 grams, that's how many grams you need if you want to get 1 mole of this sodium carbonate. All right? Now what I can do is I can find out how much of that 106 grams is from the sodium. How much is from the sodium? And that would just be this portion, right? The 2 times the 23, or 46. So I put the 46 over 106, right? And that would give me the fraction. And then I multiply by 100, and that gives me my 43.38%. Okay? So, when we say percent composition, we're talking about the mass of the element that's contributing to the total mass. Does that make sense?
I think you lost me there. I caught the 46 over the 106.
Yeah, because this 46 is from the mass of the sodium, right? And this one down here is the total mass.
And then just explain to me how we get from that to 43%.
Well, then we multiply it by 100. Because if you just take the mass, I don't know if you can see the calculator here.
Yeah, I can see it.
Okay. So if we take the 46 and divide by 106, that's just going to be the fraction, 43.39. But if we multiply that by 100, then that gives us not out of 1, but out of 100, right? So it's 43.39.
Okay, I guess I didn't understand that. We go ahead and divide and then multiply by 100.
Yeah, we divide by the total mass and then times 100. So 106 was the total mass. If we take the 12 divided by 106, right? So we take the 12 and say that's the mass that the carbon is contributing. Divided by 106 times 100, there's 11.3%. So it's 49% sodium, 11.3% carbon. And we can do the same thing for oxygen, 3/16, that's 48 divided by 106. and we're going to get 45.29%. And of course, the sum of all the percentages of the elements add up to 100%, right? All the elements in a compound, their individual percentages, their individual percent composition adds up to 100%.
Can you show me the paperwork on that again?
Which one? The oxygen?
Yeah, just the last one that you presented.
Okay. So
I mean, you don't have to write it down. Just show me what you already have. I just want to take a screenshot of the.
Whoops.
Okay, there we go. Yeah. Okay. Let me just.
An example here of calculating the percent composition of carbon in carbon dioxide. All right. So how would we do this? What would we do?
So we look on the chart and carbon is 12.
Mm-hmm.
And oxygen is 16, and we have 2 of those. And so we would have.
That's 44.
That's okay.
All right. 44. Now what do we do?
And we're looking at the percentage of carbon, so we would divide the 12 by 44, yeah.
Okay, very good.
And after we divide that, we would multiply it by 100.
All right, so I'm getting 27.27%. Okay, very good. So we determined the mass, the molar mass of the compound, and we determined what contribution the carbon is, right? And then we get 27.29%. And from that, we can also know the mass of the oxygen is 100% minus the 27.29, right?
Okay.
Now, different kinds of problems, they'll say something like this, where they just say, here's a sample that we analyzed and found 2 different elements, nitrogen and oxygen, for example, 0.1417 grams of nitrogen, 0.4045 grams of oxygen. And the question is, what's the percentage composition of this compound?
Okay.
Well, in this case, how are we going to get the total if we don't know the chemical formula?
Could we?
Could we just add those 2 together?
Yeah, could we add those 2 together and then we just divide by whichever element we're looking for?
That's right. That's right. So we just take the 0.1417 for the nitrogen and divide that by the total and times 100. And then could do the same thing. We could take the 0.4045 divided by the total times 100, and that would give us the percent of oxygen. Okay, very good. Here's another example that we have to kind of be comfortable with, even though this is a kind of an old-fashioned way, and maybe everybody knows how to do it. There's a few out there that don't remember how to do this sort of thing. But we have to think how to answer a question where it says, if I have a 35.5 gram sample and I find that it's 23.5% silicon, right? So here's a pile of some sample of material, a total of 35.5 grams, and we're trying to find out what percentage of that is, trying to find out how many grams of that 35.5 is silicon if we're told that it's 23.5 grams, 23.5% silicon. Okay?
Yeah. Is it okay if we do the long way? I think that would work with the equal sign first.
Oh, that one there?
Yeah, could we do it like that?
Yeah, we could. We could. In this case, it's a little bit hard to come up with the conversion factor. But what we're after,
Okay.
we're after grams of what?
Silicon.
That's right, grams of silicon. And we have a total mass of 35.5 grams of sample. All right. And now we need to relate grams of sample to grams of silicon. Any ideas? How can we relate grams of sample to grams of silicon? What does this 23.5% mean?
Yeah, so we have, we would put that on top, the 23. Over the 1.
Well, that would be 23.5 grams of silicon if you had
over the total
100 gram sample.
100 grams. Yeah.
Right? Because that's what that means,
see.
is percentage.
Gotcha.
Very
Yeah.
good. And then that would be how we would get our answer, right? We would just take our 35.5 and then we would multiply it by the 23.5 and then divide by 100. So that's 8.34. Okay, good. So that gives us our answer. All right. So I'm going to introduce a new name for, well, we know about molecules. We've talked about molecules. Those are compounds that contain only nonmetals. And the formula for a molecule we can call the molecular formula. And I'm going to introduce to you a new concept called the empirical formula for a compound. And the reason why I'm doing it is because when you use analysis of materials to find out the amount of the different elements in a material, in the end you get what's called the empirical formula. You don't get the molecular formula necessary, and that's because the empirical formula is the simplest ratio of elements. The molecular formula, like for glucose, for example, C6H12O6, is not the simplest whole number ratio. This is how the molecule actually is composed, what it looks like, how it goes around in solution, right, or in solid or liquid phase. However, this is the empirical formula. And you see that to get from C6H12O6, everything is divided by the greatest common multiple, and you get the minimized ratio of the different elements in the compound. Okay? So the molecular formula is what the actual formula is, but the empirical formula is the reduced form. Okay? So, the way we get the empirical formula is from information about the masses of the different elements in the compound. All right? So if we have a chemical and we know how many grams of the different elements there are in that compound, we can use that mass information, or if it's percentage composition information, which is also mass, you can use that mass information to know the number of moles of the elements in the compound. And again, the empirical formula is just a ratio of the moles of the different elements in the compound. So, here we go. We have a 2.012 gram sample of a compound, and it contains 0.522 grams of nitrogen and 1.490 grams of oxygen, and we would like to calculate its empirical formula. All right, we'd like to calculate its empirical formula. Now, I can't take the nitrogen, so this is what we want, right? In the end, we want to have the chemical formula, nitrogen and oxygen, and we need to know X and Y, right? That's what an empirical formula is. But I can't take the nitrogen and put on it right now 0.522 and the oxygen 1.490, right? Because even though those are the masses of material that they said in the problem, an empirical formula isn't an expression of the masses of these materials or these elements. It's an expression of the moles of these elements. So we don't take the masses and put them down there. We do have to solve for these values, these X and Y's, from the masses of the different elements. So nitrogen is 0.522 grams of nitrogen, 0.522 grams of nitrogen, and I want to get moles of nitrogen. So I'm going to convert my grams of nitrogen to moles of nitrogen using a conversion factor. What has to go down here?
Grams.
Yeah, grams of nitrogen. And up here?
Moles.
Moles. Moles of nitrogen. Whoops. So, do you know how many grams there are in a mole of nitrogen?
That's the atomic weight.
Yeah, that's right. It's number 7 and
14.
yeah, 14. 14. Whoops. 14 grams for every 1 mole. Try that again. 1 mole there. 14 grams for 1 mole. So the calculator has to have the 0.522 and then divided by the 14. Very good. 0.0373. Now that's moles of nitrogen. Okay? So I can take that 0.0373 and use it as my moles in my empirical formula. Now I still need the Y here, but I can put the N there. Now it's not quite done because we want to have a whole number, right? But we get closer. So now the 1.490 grams of oxygen, we want that in moles again because we want moles of oxygen up here so we can get our empirical formula. And then we go from grams of oxygen to moles of oxygen, and there are 16 grams per mole. And so if we use our calculator, 1.490 divided by 16, 0.0931. And I'll put that here, 0.0931 moles of oxygen. All right, so now I have nitrogen, 0.0373, oxygen, 0.0931. Now, how are we going to get closer to the empirical formula? These are moles, but why is it not quite the empirical formula?
Because we need a whole number.
Whole numbers, that's right. And we can get whole numbers by dividing both of these by the smallest of these two, right, which is the 0.0373. And I chose that because what it's going to do is it's going to force one of them to become 1 right away, right? And so that's good. So then we got N, that's going to be 1. Whoops, 3, not 2, 3, but 373 there. N, 1. Now I'll do the oxygen side, the 0.0931 divided by 0.0373, and that's 2.49, which is close to 2.5. Very good. Now, I'm still not quite there at whole numbers, but it's pretty clear what I can do to get to whole numbers now, right? What can I do? What could I do to get 2.5 to be a whole number?
Double it?
Yeah, that's right. Multiply it by 2. Now, if I do that, I also have to multiply the nitrogen by 2, right? But now I have the ratio in moles of nitrogen and oxygen in whole numbers And it's the same ratio up here that I had before as well, that I got from the masses of the materials to start off with. Okay, very good. So I got N2O5 as my empirical formula. Again,
Could we also write, oh, I'm sorry.
Go ahead.
Could we also write that with just the 2 in front of the N and have the oxygen still 2.5, or do we never want to write it with
the coefficient?
Right.
No, we don't want to write it with the coefficient. The coefficient just tells us how many of these units we have. It's not telling us necessarily the ratio of the different elements in the compound. So we identify the ratios of the elements, and then you can use the coefficients to tell us if we have more than one of them. Go ahead. What was that?
Can we pause?
Sure.
Can we pause?
Yeah. So when we look at the empirical formula for a compound and compare it to the molecular formula, and if we use our glucose, now we didn't kind of emphasize what chemical we were talking about before, but the C6H12O6, that's the chemical formula for our glucose, C6H12O6. This is the molecular formula, but, and I'm going to write a little MF there to remind us that that's the molecular formula, but it's not the empirical formula. So could you tell me what the empirical formula for this compound is?
So would be CH2O.
That's right. That's the empirical formula. It's the reduced relationship or molar ratio of the different elements in the compound. Now, we said before, and we're reiterating in this slide, that there is a multiplier or a number that if you multiplied this bottom by, you can get that molecular formula, right? You multiply the empirical formula by some number, all of these values down here, and you get the molecular formula. And what is it for the empirical formula of glucose?
It would be 6.
That's right. If we multiply the bottom here by 6, then we get the molecular formula. And that same number can relate what we call the empirical mass. Whoops, not just 2 bumps. The empirical mass of the compound to the molecular mass of the compound. Molecular mass. Now we find the empirical mass by just looking at the mass of that there. Let's see, 1 carbon is 12, 1 oxygen is 16, 2 hydrogens, that's 1, 2. So 16 plus 12 plus 2 plus 16, that's 30. 30. Okay? That's the mass of this empirical formula, and we call it, what does EM stand for?
Empirical mass?
Empirical mass, that's right. We call it the empirical mass. Very good. Now, what do you think the molecular mass is? Any ideas?
180.
180, very good. How did you know that?
Multiplied by 6.
Multiplied it by 6. Because the same multiplier that exists here is going to exist between the empirical formula's mass, and the molecular mass, or the molecular formula's mass. Right? Good. So, another way to think about it is if I took the the molecular mass right here, 180, and divide it by the empirical mass, that's another way I could identify what the multiplier is, right? I could identify what the multiplier is. And that way, if we were given the molecular mass and the empirical mass and the empirical formula, but we didn't know the molecular formula, we could use the multiplier to find the molecular formula. And that's what our next example is going to do. Okay? So here it is. If we have an empirical formula of this chemical, hydrazine, and it's NH2. NH2. That's the empirical formula, NH2. Okay? And the molecular mass, not the empirical mass, but the molecular mass. The molecular mass is 32. So what is the molecular formula? Well, if we knew the empirical mass, we could compare it to the molecular mass, right? And learn the multiplier, right? But we don't have the empirical mass provided, but we do have the what? What is NH2?
It would be 14 plus 2 of the hydrogen would be 2. So 14 plus 2.
14 plus 2, that's 16. And that 16 would be what we call the what? The empirical mass, is that right?
Okay.
And NH2 was our empirical formula. So we have our empirical formula of NH2, and we have our empirical mass of 16. Now, we are told that the molecular mass is 32. If the molecular mass is 32, how is that going to help me identify what the molecular formula is?
So we see that the relationship between the empirical mass is 1/2 of the, so we would multiply by 2, right?
That's right. Multiply by 2. So to get to the molecular formula, what would we do?
So we're going to multiply that by 2.
That's right. So what would our molecular formula be?
And N2H4.
Very good. N2H4. Excellent. So we were given information about the empirical formula. We were given information about the molecular mass. We got the empirical mass just from the empirical formula, right? And so all that information allowed us to identify what the molecular formula is. Okay. This substance is known to be 35% nitrogen, 5.05% hydrogen, and 59.96% oxygen. How are we going to find that empirical formula? What is the empirical formula again? Do you remember? What's the definition for the empirical formula, kind of?
It's the least amount.
Simplest ratio?
Yeah, simplest ratio.
Uh-huh. Of what? In terms of grams or in terms of moles?
In terms of moles.
In terms of moles. But when they give us percentages like this, what are they talking about? Are they talking about 35% in terms of moles? 35% nitrogen, 5.05% hydrogen? What did we say percentage was?
I thought they were saying in terms of moles, but
no. Remember,
since we have the mass down below, I guess it's mass. Huh?
Percentage is always expressed in terms of mass. In terms of mass.
Well, it is.
Yeah. So what this is basically saying, I have a compound made of nitrogen, hydrogen, and oxygen, right? I can draw a pile of this compound. Here it is. It contains nitrogen, hydrogen, and oxygen. And if I had 100 grams of it here, if I have 100 grams of it, that means that 35 grams of it is nitrogen, 5.05 grams is hydrogen, and 59.96 grams of it is oxygen. Okay? So, can I take my chemical formula N Y HXOZ? There's my empirical formula, and I'm trying to find those. Can I take the 35 and put it down here? And the 5.05, put it down here for hydrogen? and the 59.96 down here for oxygen. Would that be okay? Why can't I do that?
Because that's percentage.
Yeah, this is mass, right? This is mass up here.
Right.
And this down here, my empirical formula is an expression in terms of moles. But
Okay.
I can convert my 35 grams of nitrogen to moles, right? And I can convert my 5.05 grams of hydrogen to moles and my 59.96 grams of oxygen. And how would we do that? What would we put to the right of our equal sign?
Okay, we're looking for moles.
Moles of which element should we do first?
Let's do nitrogen.
Okay, moles of nitrogen. So we start with what?
So we're going to start with, we know that we have 14 basically 14 grams of nitrogen
For 1 mole?
for 1 mole.
That's right. And I could use that here. I could say 14 grams for every
okay.
1 mole of
So I'm
nitrogen.
getting ahead of myself. Okay.
I mean, we could have put it over here, but the concern would only be that if we put the 14 on top because we don't know which place to put it, then we might not end up with the moles on top, right? So it would be fine if we put the 1 mole of nitrogen and 14 grams of nitrogen. But typically we start with what they give us, which in this case is the 35% or 35 grams of nitrogen.
I see.
Okay, good. So I'll do that on
And-
my calculator. What's that?
And nothing goes underneath that 35, right?
That's right. That's just what we start with. You can think of it as 35 grams of nitrogen per sample. And then this is how many moles of nitrogen there are per sample, if you wanted to. Okay, so we got the moles of nitrogen. Now let's get the moles of hydrogen.
Okay. So we can, with the equal sign, okay, so now we can start with the 59.96. Okay, I'm on the left, right?
Okay, over here, 59.96. Where'd you get that from? Whoops.
From on top,
Okay, what is that?
and that's the percentage of oxygen.
Oh, percentage
Oh,
of
I'm sorry,
oxygen.
I'm looking at high. I mean, that's the, wait.
That's all right. We'll go oxygen first.
Can we? Okay.
Yeah, sure. All right, so we go from grams of oxygen to moles of oxygen.
And the moles of oxygen, we look below and we see that it's 16.
Yeah, 16 grams for every 1 mole. All right, I'll do that on the calculator. 59.96 divided by the 16, 3.75 moles of oxygen. All right, last one here, moles of hydrogen.
Okay, so the equal sign, and we're looking at moles of hydrogen.
Mm-hmm.
And so we're looking at on top 5.05%.
Yeah, or 5.05 grams of
hydrogen.
hydrogen. Very good. Now remember that
And-
percentage, we can take it as grams because you can always assume you have a 100-gram sample, for example, right? And
Okay.
therefore, you can use those percentages just as grams. Okay?
So what in the, you may have to pause this, but what in the,
So now you might wonder, how did we know that these percentages were actually in grams and not in moles? Well, that's what we're trying to help you understand right now, is that we never express percentages in anything other than grams. So when we express information in percentages, it's always expressed in grams. Or in other words, 35% nitrogen means if you have 100 grams of that material, 35 of those grams will be from the nitrogen. Okay, good. So we have 5.05 grams of hydrogen. And now we got to convert our grams of hydrogen to moles of hydrogen. That's an easy one, right? It's just 1, right? So that's our 5.05. So now I have my 2.5 for the moles of nitrogen, 3.75 for the moles of oxygen, and 5.05 for the moles of hydrogen. And I'm going to write down an empirical formula then for us. Nitrogen, 2.5, hydrogen, 5.05, oxygen, 3.75. Did I do that right?
Okay.
2.5, 3.75, and 5.05, yeah. Now, how do I get it to a whole number ratio? Because that's the molar ratio, but it's not in a whole number ratio yet.
So we divide it by the lowest number there.
Okay, so that looks like the 2.5. 2.5 divided by 5, n will be 1 there. Here, I'm going to get H2. Wait, 5.05 divided by 2.5. Oh, yeah, that's right, 2. And then O, 3.75 divided by 2.5. That is 1.5. 1.5. So let me rewrite that. NH2O 1.5. So I didn't quite get there, right? What do I got to do now?
So if we I guess if we double it.
That's right, because this is 5.5, right? So that would make the oxygen 3, the hydrogen 4, and the nitrogen 2. N2H4O3. Let's see if that's one of our answers. Or I guess it's not an ABC question. But N2H4O3, that is our answer. Okay, very good. So we just did a couple problems here. This one, we looked at the empirical formula and the molecular mass, and we got the molecular formula. This one here, we got the empirical formula from the masses of the different elements, or the percentage composition of the different elements. Now, we're asked to determine the molecular formula of this compound. So we know that the empirical formula is N2H4O3, and we want to determine the molecular formula of the compound. Now, they do tell us that the molar mass of the compound is 80.06. So, how can we determine what the molecular formula for the compound is? What do you think?
Okay, so I'm just trying to process the example again. So substance.
We got the empirical formula here now.
We already got that. Okay.
N2H4O3. Now, what's the relationship between the empirical formula,
The empirical formula
and the molecular formula? Do you remember?
Yeah. So now we're the empirical is dealing with moles.
Uh-huh. And it's the simplest ratio, right?
Right. And so now we need to convert that to mass.
That's right. We need to know the empirical mass. The empirical mass. So you tell me the numbers and I'll add them up.
Okay, so for nitrogen.
That's 14. I know that one. 14. 14.
Okay, 14.
Twice. 14 plus 14.
Twice.
Plus what?
And plus 4 of hydrogen's 1,
Okay.
so plus 4.
Plus 4.
And then oxygen 16 times 3, that's what, 48?
Yeah. Okay, so the
So
total
plus 48.
the total is 80.
80, okay.
So we found, what is
Well, I
that?
guess we already got that down below, okay.
Well, no. That was the empirical formula. But you're right, that down below they told us that the molar mass is also 80. So what does that mean? That means that the empirical formula is also the what?
Empirical mass.
It gives us the empirical mass, but the empirical formula is also the molecular formula.
Oh,
The molecular formula,
okay.
right? And that's possible, right? It's possible for the empirical formula to actually be the molecular formula. And again, we knew that because we found that the empirical mass was the same as what they gave as what they called the molecular mass. Okay, very good. So here's another question. We're given the percent composition. Now, we're not going to go over these two, but these are good practices for the folks at home.
Dan, can you pause a second?
So I'll let everybody have a chance to solve this one, and then I will, so I push pause now if I were you trying to solve it, and then I'm going to reveal the answer now to you in 2 seconds. 1, 2, all right. So the answer is D, CHCl, okay? We use these percentages here as masses and converted those masses to moles, and then we find the simplest whole number ratio of those moles for carbon, hydrogen, and chlorine, and that's how we get our empirical formula. All right, now here's another question for you. Very good practice problem. So why don't you guys take time to do this one? Push pause, try to find the answer. I'll tell you the answer for now, okay? In 2 seconds. So if you haven't pushed pause yet, 1, 2. All right, so the answer here is A. So the way that we did that is we took the empirical formula, CHCl, added up the mass that you get, 1 carbon, 1 hydrogen, 1 chlorine, 12, 1, 35.45, right? Those are the masses of our different elements in there. So that's the mass of the empirical formula. And compared that to the molar mass, which was provided as the molar mass. The molar mass divided by the empirical mass gives us the multiplier. And so we could take the empirical formula and multiply it by that multiplier to get the molecular formula. Okay, very good. Now we're going to go over an example of how they identify how much carbon and hydrogen is in a compound. All right, and they do that by taking the compound. Generally, what they're interested in looking at is some organic compound and combusting the organic compound. Combustion is a fancy word, but it really just means combining something with oxygen, all right? And this something is going to be an organic compound where it's made mostly of carbon, hydrogen, and maybe some oxygen and something else, but generally mostly carbon and hydrogen. And combustion means combining that organic compound with oxygen gas. And when you do that, the products are carbon dioxide and water. The carbon here goes with the oxygen to form carbon dioxide, and the hydrogen in the compound goes with the oxygen to form water. All right? So this is an example of combustion. And in a combustion reaction, you allow the compound to interact with the oxygen in a tube like this, some sort of container, with heat provided. And just like paper or wood, if you get it hot in the presence of oxygen, it will burn. And when it burns, it produces carbon dioxide and water. And if you have oxygen continually flowing through this system, the produced carbon dioxide and water will be funneled down this plumbing, and it will try to get it to escape. But before it escapes, all of the water will be absorbed by an absorptive material here. And all of the carbon dioxide will also be absorbed by a different material. Then you can tell the masses of the water and the carbon dioxide that was produced from this reaction by weighing the mass of our little glassware here, our U-tube, before the reaction and after the reaction. All right. We also have more complex methods for identifying amounts, concentrations of other chemicals, other elements like nitrogen, sulfur, chlorine, and so forth. Okay, so once we know the mass of our carbon dioxide, we can use that mass of carbon dioxide to calculate the moles of carbon dioxide and then the moles of carbon. And because the carbon in this reaction all came from this spot, if we know the moles of carbon over here, we know also the moles of carbon over here. And we can calculate the empirical formula, because that's what the empirical formula is, and it's an expression of the moles of the different elements in a compound. Okay? So, here's an example. We took a 5.217 gram sample of a chemical and we combusted it. All right? So here is our mosquito. Here's our compound here. We have 5.217 grams of our compound. And when I burn it in the presence of lots of oxygen, how much carbon dioxide do I get?
7.406 grams.
Yeah, 7.406 grams of carbon dioxide. How much water?
4.512 grams of water.
Very good. So from that information, from the grams of oxygen and the grams of water, I can, because this is the chemical formula, right? It's a very general chemical formula, but in general, you take a carbonaceous material that has carbon and hydrogen, burn it, it'll produce carbon dioxide and water. And therefore, from the resulting mass of carbon dioxide, we can calculate the moles of carbon dioxide, relate that to the moles of carbon, and know that the moles of carbon must have come from this compound there. So the moles of carbon that you have here is equal to the moles of carbon that you started with. Okay? So I'm going to calculate. Now I want the empirical formula again. So to the right of my equal sign here is going to be moles of carbon by starting with my grams of carbon dioxide, 7.406 grams of carbon dioxide. Now I'm going to go from grams of carbon dioxide to, what do you think? Any ideas?
To carbon?
Almost. I'm going to go to moles of carbon dioxide. Moles of carbon dioxide.
Oh, yes.
And then I go from moles of carbon dioxide, then I go to moles of carbon. Right? And that's what I want to have. I want to know how many moles of carbon are from my 7.406 grams of carbon dioxide. Now, do you remember how many grams of carbon dioxide there are per mole of carbon dioxide? We have to add it up, don't we? 2 oxygens are 16. So that's 32. Plus the 12. 32, 42, 43, 44. So there's 44 grams of oxygen per mole. Right?
Okay.
How about how many moles of carbon are there for every mole of carbon dioxide? If I have a mole of carbon dioxide, how many moles of carbon does it have in it?
Just one.
Just one. So that's a 1-to-1 ratio there. Very good. So I just have to take the 7.46 and divide it by the 44. I'll do that on my calculator here. Uh, 1.1695. Whoops, 95. moles of carbon. All right, now I do the same thing for moles of hydrogen. What am I going to start with this time to get the moles of hydrogen?
We'll start with, where is it? Let's see. Okay, so the total grams, I guess, right?
I'm going to start with grams of water, right? Because all of the hydrogen relates or went to the water, right?
Oh, yeah, okay.
So that's 4.512 grams of water. Very good. So I go from grams of water to moles of water, right? And do you know how many grams of water there are in a mole of water?
Yeah. Oh, gosh. Danny, can we pause?
Sure. Okay, so that's 18 grams of water. The oxygen's is 16. Hydrogen, 1 each, 17, 18. 18 grams for every mole. And now I'm in moles of water, H2O, and I need to go to moles of hydrogen. All right. And now I have to look and see how many moles of water are there in 1 mole of hydrogen, or water. Sorry, how many moles of hydrogen are there in 1 mole of water? Well, 1 mole of water, H2, there's 2 moles of hydrogen. So then I just have to take my 4.512 divided by 18 and multiply it by 2. So that's just calculator work. 4.512 divided by 18 times 2. And the answer is 0.5013 moles of hydrogen. So the empirical formula of this compound looks something like this we've learned so far. CXHYOZ. It has oxygen in it as well. And the moles of hydrogen we solve for, the moles of carbon we solve for. So C, I'm going to put 0.1695. For hydrogen, 0.5013. Now, where do I get the moles of oxygen? I can't use the grams of carbon dioxide or the grams of water or both because I don't know if the oxygen went with carbon dioxide or went with the water, or if the oxygen that went with the carbon dioxide or the water actually came from my compound. All right, so I don't know. The only way I can tell the amount of oxygen is by taking my initial mass of material, which was 5.217 grams. I could take the 5.217 grams and I could subtract the grams of carbon and grams of hydrogen, and I would know that the rest is grams of oxygen. So if I took the 5.217, that's grams total, we could call it, and I subtract grams of carbon and subtract grams of hydrogen, the result would be the grams of oxygen. Now, I don't have the grams of carbon and I don't have the grams of hydrogen, but I do have the moles of carbon and the moles of hydrogen. So I can convert the grams of hydrogen, the moles of carbon, 0.1695, I can convert that moles to grams of carbon. 1 mole of carbon is 12 grams of carbon. So 0.1695 times the 12, right? That tells me I have 2.034 grams of carbon. Do the same thing for hydrogen. I want to know grams of hydrogen. And I know I'm going to start off with my 0.5013 moles of hydrogen, 0.5013 moles of hydrogen. And I can go from moles of hydrogen to grams of hydrogen. And that's a 1-to-1 ratio. That's nice. So it's 0.5013 grams of hydrogen. So from my total moles, my total pile of material there, which was 5.217 grams, I subtract my grams of carbon, 2.034, and my grams of hydrogen, 0.5013. Now that looks like the moles of hydrogen, but it's the same because it's a 1-to-1 ratio, right? 1 gram of hydrogen is 1 mole of hydrogen. Subtract those two. I'll do that in my calculator here, 5.217 minus the 2.034, and then subtract the 0.5013, and I get 2.672. 2.673 actually. And that is my grams of oxygen. Now I did all of that because I need that grams of oxygen to find the what? Do you remember what we're looking for?
Yeah, find the mole.
Moles of oxygen. That's right, moles of oxygen. Very good. So I can go from grams of oxygen to moles of oxygen, 16 grams for every mole. So my 2.673, I just have to divide by 16, and I get 0.167 moles of oxygen. I have myself my empirical formula, almost, right? That's called the empirical formula, almost. Because now I have to divide everything by 0.1695 or 0.167, I guess. Looks like they're about the same number. So we're going to have C1H. What's 0.503 divided by 0.167? 0.5013 divided by 0.1670. That's 3. 3. So CH3O, that is my empirical formula. And that's what they asked me to do. What's the empirical formula? I found those masses of material, and CH3O is my empirical formula. Okay, very good. So we'll have another one to practice next time where we try to find the empirical formula. Actually, I'll let you guys, well, yeah, I'll let you guys do this one right now. So why don't you try to solve this problem? Look back at the example we just did and try to solve this problem. I'm going to show you what the answer is, and then if you have any troubles with it and you want to talk about it further, if you can't figure out from the previous example, come and talk to me. Send me an email. Okay. Hopefully you had a chance to look at it. I'm going to show you the answer here in 2 seconds. 1, 2. All right, so the answer is A. Okay.